So let's have Newton's laws of motion. This is our first example. Okay. So we have two forces acting on a particle whose mass is 2 kilogram. Okay. Which is initially at rest. And the coordinates are given there. For letter A, it was asking for the components of the particle's velocity at time is equal to 10 seconds. Letter B, in what direction is the particle moving at that time? Letter C, what the displacement does the particle undergo during the first 10 seconds? And letter D, what is the coordinates for the final position? So let's start with letter A. So let's identify the given first. Alright, so what are the given parameters? Let's have F1, which is equivalent to negative 6 I hat minus 4 G hat newtons. F2 is negative 3 I hat plus 7 J hat newtons, right? And the mass of the particle is 2 kilograms. Okay, and the initial coordinates are negative 2 I hat plus 4 J hat meters. Okay, so for letter A, let us solve for the resultant or the net force. So the net force is equivalent to F1 plus F2. So we have negative 6 I hat 4 J hat newtons plus negative 3 I hat plus 7 J hat newton. So we just simply add those values with the same coordinates or the axis. So we have negative 6 I hat minus 3 I hat. We have negative 9 I hat. Again. Next we have negative 4 J hat plus 7 J hat. We have 3 J hat. And this is in newtons. This is our net force. Now, using the second law of motion, the summation or the net force is equivalent to mass times acceleration. Okay, and from this formula, we can get the value of the acceleration as the summation of the force or the net force over m, which is equivalent to negative 9 I hat plus 3 J hat, this is in newtons, over 2 kilograms. Okay, so we have negative 4.5 I hat plus 1.5 J hat meters per second squared. And then for the final velocity, we're gonna be using the formula for acceleration. So that's change in velocity over change in time. Okay, so therefore Vf minus Vi is equal to A times T. Okay, and we know that it was from rest, so therefore this is 0. So Vf is then equivalent to acceleration times time. Okay, so when time is equal to 10 seconds, Vf is equivalent to negative 4.5 I hat plus 1.5 j hat meters per second squared, right, multiply with 10 seconds, so giving us final velocity as negative 45 I hat plus 15 j hat meters per second. That's our answer for letter A. Next, for the direction, okay, we're gonna be using theta is equivalent to arctangent of Vy Vx. We're just gonna be using the direction as well. So we have arctangent of 15 over negative 45 meters per second over meters per second, so that will be cancelled out, and our angle would be negative 18.4 degrees. Okay, if we're going to analyze this, our final velocity is located at the second quadrant because we have negative x coordinate and positive y coordinate. So if the angle that we have solved is this one, therefore to get the direction, okay, so alpha is equivalent to negative 18.4 degrees plus 180 degrees, which is equivalent to 162 degrees. That is already the final answer, or you could also say that it is 162 degrees from the positive x-axis, etc. Next, for the displacement, we're gonna be using delta x. Can I use r instead? Okay, so that's for my displacement in two-dimensional. Right, it's equivalent to VIT plus 1/2 a t squared, but this is a two-dimensional vector, so therefore we have two solutions. For the x displacement, or the displacement on the horizontal axis, we have delta x is equivalent to, since Vi is 0, we're left with 1/2 ax t squared. Okay, and ax is equivalent to negative 45, negative 4.5 rather. So we have negative 4.5 meters per second squared multiplied with time, which is 10 seconds, raised to the second power. So the change in x is equivalent to negative 225 meters. Okay, and for the y displacement, okay, so we have delta y is equal to 1/2. We're going to be using the y component of the acceleration now. Okay, so we have 1/2 and then positive 1.5 meters per second squared times 10 seconds raised to the second power. So therefore, delta y is equivalent to 75 meters. Okay, so we already have the x and y components of the displacement. Therefore, the change in displacement is equivalent to negative 225 I hat plus 75 j hat meters. Next, the coordinates of the final position. Okay, so delta r is equivalent to rf minus ri. Okay, so therefore rf is equivalent to delta r plus initial coordinates. Our change in the displacement is and our initial coordinates are okay. So therefore RF is at negative 227 I hat plus 79 j hat meters. And that's it for our item number 1. So here is our second item. We have an iron bolt with a mass of 65 grams hangs on a string whose length is 35.7 meters. Now, the top end of the string is fixed. Okay, so without touching it, a magnet attracts the bolt so that it remains stationary, but is displaced horizontally for 28 centimeters to the right. Okay, so the magnet is located at the right of the bolt on the same vertical level as the bolt in the final configuration. Now, we have to draw the free body diagram of the bolt. Okay, letter B, find the tension in the string, and letter C, find the magnetic force on the bolt. So, let's state the given parameters. So first, we have the mass of the iron bolt as 65 grams. Okay, the length of the string as 35.7 centimeters. The displacement horizontally, which is 28 centimeters. Yeah, that's it. So letter A, let's draw the free body diagram. So it's like there is our wall or ceiling, and we have this string, and this is our iron bolt, right? So, and then a magnetic force. So let's say from here. So let's draw line 35.7. Okay. Yep. So here's our bolt now. Okay. And the displacement is yep. So let's say the displacement is 28 centimeters and the length of the string is 35.7 centimeters. So this is also 35.7 centimeters. So we have that angle of inclination, right? And if we have the string, therefore we have this tensile force, right? And magnetic force is pulling this iron bolt to the right. So this is our magnetic force, right? And the bolt also has a weight. That's it. So this is our free body diagram. Okay, and we can actually solve for the angle of inclination. So to solve for the angle of inclination, we're going to be using cosine theta. Okay, so cosine theta is equal to adjacent over hypotenuse. So, right, so our adjacent side would be 28 centimeters over the hypotenuse of 35.7 centimeters. Therefore, theta is equivalent to 38.3 degrees. So, letter B. Find the tension in the string. Okay, so since this is in equilibrium state, okay, there is no motion. Therefore, acceleration is 0. So, the summation of force, assuming forces going to the right are positive, is equal to ma sub x, but we don't have an acceleration. Okay, therefore, it is equal to 0. Okay, so what are the horizontal forces? Okay, first, we have the magnetic force, and then the x component of the tension. So we have T, that's negative because going to the negative x-axis direction, cosine theta is equal to 0. Okay, but we do not have the value of the tension nor the magnetic force yet. So this is our equation number 1. Okay, so now let's have the vertical forces, assuming upward forces are positive, which is 0. So therefore it's 0. And what are the vertical forces? The y component of the tension, that's positive, and then the weight, which is equal to 0. Now, it's equal to weight over sine theta. And weight is equal to mass times gravity. Okay. And mass of the bolt is 65 grams. 0.65 kilograms. Let me transfer that here. Okay, over multiply with 9.8 per second over sine of 38.3 degrees. Therefore, our tensile force is equivalent to 1.03 newtons. So that's the answer for letter B. Okay. And for letter C, use equation 1. So to solve for the magnetic force, this is actually the x component of the tension. Therefore, the magnetic force is equivalent to newtons. So it's positive, therefore it's That's it for this. Our third example. We have this bag of cement which is in equilibrium state, okay, and as you can see on the figure, we have the T1, T2, and T3, and we are asked to find the values of these three tension or tensile forces given angle theta 1 and theta 2, okay, and also the weight of the cement is also given. So this is equivalent to 325 newtons. So if we're going to get the free body diagram, okay, so we have here our T2. Here is T3 and T1, and this is our T3. Okay, and if this is our horizontal axis, therefore this is our theta 2 and this is our theta 1. Okay, opposite internal angles are equal, right? Now let's try to solve them. By the way, theta 2 is equivalent to 40 degrees and this is 60 degrees, right? And let's start. Okay, so if from this point, okay, we only have two forces acting on the cement, which is the weight and the tension. Therefore, T3 is equivalent to the weight, which is equivalent to 325 newtons. Okay, that's our first FBD. Now, looking at the second FBD, this one. Okay, so let's have, since this is in equilibrium state, therefore the summation of forces is equal to 0. So we have summation of forces on the vertical axis assuming upward direction are positive is equal to 0. So what are the vertical forces? First, let's have the y component of T1. So that is T1 sine theta 1 plus T2 sine theta 2, which is equivalent to T3, or let's just name that as our FG. Okay, and then so this is our equation number 1, summation of forces on the horizontal axis assuming forces to the positive x-axis are positive is equal to 0. So we have the cosine theta 2 x component of T2, okay, minus the x component of T1 is equal to 0 because those are the only forces on the horizontal axis. Okay, therefore, T2 cosine theta 2 is equal to T1 cosine theta 1. And this is our second equation. Okay. Looking at our two equations, we have two equations and two unknowns. Therefore, we can solve for the values of T1 and T2. Okay, so let me arrange it. So we have T1 sine 60, T2 sine 40 is equal to 325 newtons. and then T1 cosine 60 no, that's 40. T1 cosine 40 is equal to minus, wait, is that 60? Okay, minus T2 sine 40 is equal to 0. Okay, so if you're going to apply your algebraic skills by substitution method or elimination method, you're gonna have T1, which is equivalent to 253 newtons, and T2 as 165 newtons. And that's it. We also have T3 here, T1, T2, and T3. Okay, next we have this item. The distance between two telephone poles is 50 meters. So let's say this is two telephone poles. Okay, and the distance between them is 50 meters. This is 50 meters. Now, when a 1 kilogram birds land on the telephone wire midway between the poles, the wire sags to 0.2 meters. So have this. And 0.2 meters is this one. Okay, 0.2 meters. Okay. Now, of course, there are tensile forces present on this one. Tension here, and the tension there. But since the bird landed midway, okay, therefore these two are just the same. Okay, the magnitude of these two tensions are just the same, but the direction are different. So this is our free body diagram. So have to put the weight of the bird, okay, which is equivalent to 5 by 9.8 meters per second squared. Therefore, weight is equivalent to 9.8 newtons. Okay, that's for letter A. Next, letter B. Now, to get the tensile force, we need to get the angle theta. Okay, so let's have this angle theta. Since it's midway, therefore this is 25 meters. Okay, and this is a right triangle. Okay, so let's use tangent. So tangent theta is equivalent to opposite, which is 0.2 meters, over the adjacent, which is 25 meters. Therefore, angle theta is equivalent to 0.458 degrees. Okay. Now, if we're gonna have the summation of forces on the vertical axis, assuming upwards direction is positive, so it's in equilibrium, therefore it's equal to 0. Okay, so what are the vertical forces? So we have two, the y component of the tension, so this is also angle theta, just the same. Okay, so that's t sine theta, and there's two of them, so let's just multiply 2 here since they have equal magnitudes anyway, minus the weight is equal to 0. Now, to get the tensile force, we have weight over 2 sine theta. It's equivalent to 9.8 newtons over 2 sine of, so therefore an object whose mass 1 is 5 kilograms, that's the one on the table, and then our hanging object has a mass of 9 kilograms. Now they're connected to a string that passes over a pulley. Okay, so letter A, let's draw the free body diagram and find the magnitude of the acceleration of the object and the tension in the string. So we have two FBDs here, so let's have FBD of M1. Okay, so what are the forces acting on M1? So first, of course, the weight. Let's have the weight. Okay, so M1G, and then we have the normal force because it has a contact on the surface, and then the tensile force. Okay, so this is the force exerted by the stream on the object. So this is our tensile. So the friction is not yet present here because it's not stated in the problem. Right? Next, the FBD on M2. Okay, so of course it has a weight. Okay, and then the tensile force, and those are the only forces acting on that hanging object. Now, that's for letter A. Letter B, let's MC. So let's solve for the acceleration and tensile force. Okay, so if you're going to analyze the FBD on M1, okay, our acceleration is going on this direction. Why? Because M2 is has a greater mass than that of the M1. So we are assuming that the motion would be from here going up. Okay. So if that's the acceleration for M1, the acceleration for M2 would be this way, right? So on M1, okay, M1, right? Analysis on M1. The summation of forces on the vertical axis, assuming upward forces are positive, is equal to 0 because we do not have an acceleration or motion on the vertical axis. So what are the forces acting on M1, the vertical axis? So we have the normal force, which is equivalent to weight 1. Anyway, we're not gonna be using the normal force, so we don't need to use this one. Okay, but we have a motion on the horizontal axis. So therefore, summation of the horizontal forces, assuming forces to the right are positive, is equal to mass times acceleration. Okay, so what are the forces acting on the object on the horizontal axis? That's tension, and then the mass is 5 kilograms times acceleration. So we have a positive acceleration because it's going to the positive direction. So this is our first equation. Okay, now let's analyze M2. So the summation of forces on the vertical axis, assuming upward position or positive, is equal to mass times acceleration. So we have tension minus W2 is equal to mass times negative acceleration because it's going south. Okay, so we have tension minus 9 kilograms. So 9 kilograms times 9.8 is equal to 9 kilograms multiplied by negative acceleration. So this is our second equation. Okay, so let's do it manually. We substitute equation 1 to equation 2. So we have 5 kilograms times A minus 9 kilogram times 9.8, we have 88.2 is equal to 9 kilograms times, that's negative, right? So therefore we have 14 kilograms times A is equivalent to 88.2 newtons. Therefore acceleration is equivalent to 6.30 meters per second squared, and our tensile force is equivalent to 5 kilograms times 6.30. Therefore tensile force is 31.5 newtons. That's it. Here is our last item. There are two objects connected by a light string that passes over a frictionless pulley, and the mass of the sphere is 2 kilograms and the mass of the cube is 6 kilograms. The angle of inclination is 55 degrees. Okay. So we're gonna be drawing the free body diagram of the two. Okay, and B, magnitude of acceleration, the tension of the string, and the speed of each object after 2 seconds from rest. Okay, so M1. What are the forces acting on M1? Okay, so first, the weight. Next, we have the string, the tension on the string. Okay, and since M2 has greater mass than M1, therefore we assume that the acceleration is going this way. Okay, so for the FBD on M2, okay, so for M2, right, so we have the tensile force, okay, going this way. That's our tensile force, the weight, and then the normal force, okay, and that's it. And then our acceleration is going on this direction. Okay, but we can translate the axis on M2. So instead, we're gonna be using this coordinate. Okay, so we're gonna be using this line, okay, as our x-axis, and this line as our y-axis. Okay, so we're gonna translate the axis. So okay, so upon translating x, and this is y. Okay, so therefore this is now the new direction of my tensile force, and this is the new direction of my normal force, and my weight goes this way. Okay, alright, and then okay, and our acceleration goes this way. Oops. How do I, here, this is our acceleration. Alright, so W1 is equivalent to 2 kilograms multiplied with 9.8 meters per second squared. So we have 19.6 newtons. Weight 2 is equivalent to 6 kilograms. Okay. That's 58.8. Right? Now, if you're going to analyze our M1, okay, M1. So we already have the FBD. The summation of forces on the vertical axis assuming upward direction is positive is equal to mass times acceleration. So we have tension minus weight 1 is equal to mass times positive acceleration. So that's P minus 19.6 newtons is equal to 2 kilograms times acceleration. This is our first equation. On M2, okay, we do not have an acceleration on the vertical axis, therefore it's equal to 0, and this is our angle theta. We have the normal force minus the y component of W2, so that's 58 point, W2 cosine theta, okay, and it's equal to 0. Okay, but we're not gonna use that because we don't have friction, so let's use horizontal forces instead. It's equal to mass times positive acceleration. Okay, so we have W2 sine theta minus tension is equal to mass, which is 6 kilograms, times acceleration. Okay, so that's 58.8 sine 55 degrees minus tension is equal to 6 kilograms times acceleration. Second equation. Okay, so we have two equations, two unknowns. We can solve for the values of acceleration and tension. So the value for acceleration is 3.57 meters per second squared. It's just the magnitude. Okay. Next, because the direction of the acceleration depends on who are we talking about. Is it the sphere or the cube? So for the tensile force, we have 26.7 newtons. Okay. Letter D. Let's have the final velocity after 2 seconds. So we're going to be using the formula for acceleration, which is F minus VI over T. Okay, and since it's from rest, VI is 0. VF is therefore equivalent to A times time. So we have 3.57 meters per second squared multiplied with time, which is 2 seconds. Therefore, the final velocity after 2 seconds is 7.14 meters per second. And that's it. Thank you for watching. Have a good day.